All right, I'm going to show you two real quick examples on factoring a GCF. I'm going to actually start with the second one. A lot of you might have a harder time finding the GCF from numbers. I'm going to take you back to a skill that you might have learned your freshman year, maybe sooner, and that is the factoring tree, or some of you may have learned the birthday cake thing, or whatever you want to call it. But it's prime factoring is what it's called. The finding the prime factor is kind of like 48. 48 is 6 times 8. And any path that you would have taken to 48, let's say you didn't realize that, but you knew 4 times 12. I'm doing the same thing here. This one up here is going to be a little more efficient and a nicer looking tree, but they'll both work. I'm going to work through this one. So 6 is 3 times 2, which is all prime numbers. And 8 is 2 times 4, which is also 2 times 2. Now, once you factor out a number, you must cross it out. And then the numbers that are across the bottom are your prime factors. In other words, 48 is 3 times 2 times 2 times 2 times 2. Okay? Now I'm going to just show you just this other way, and I will erase it. If, let's say, you didn't realize 6 and 8, but you chose 4 and 12, which is the same thing, you'll see it's going to come out to the exact same numbers. They're just going to be in different orders. So it'd be 4 times 3, and this is 2 times 2, and then there we have exactly the same thing. 1, 2, 3, 4 2s and a 3. This one has 1, 2, 3, 4 2s and a 3. So I think a lot of you, I know your Algebra 1 teachers taught you the factoring tree, or you might have been taught the birthday cake method. I'll show you that one on the 18. I don't really care for that one as much just because it takes up more room. But what we do is we do 18. And if we can divide by 5, 3, or 2, well, I know I can divide by 3, and then the result is 6, which can also be divided by 3, and the result is 2. The factors of 18 are anything on the outside of the birthday cake. The 3, and the 2. Some of you may have been taught that. I don't really care for that, so I'm going to show it the other way just to make sure that we're clear on this. Choose the method you want, but 18 is 9 times 2 and 3 times 3. So this takes a little more time in finding the GCF, but the thing that's nice is it not only gives you the GCF, but you can also see what's left as well. Here's what I mean. I see that they clearly share 1, 3, so that can go on the outside. I can see that they share 1, 2, that can go on the outside. And that's all they share. This one still has a 3 left. This one still has 3 2s left. But all they share is the 3 and the 2, so it gets to go on the outside. Now, the thing that's nice about the factoring tree method is whatever you did not factor out has to stay. In other words, 2 times 2 times 2 is 2 to the 3rd power, has to stay. 2 times 2 times 2 is 8. And then the 18, what's left is only the 3. And you notice I'm leaving space here because I'm going to be dealing with the variables as well. So all I have left of this one is a 3. So let's just look at the numbers here. The factored version is 2 times 3 is 6. We still have an 8 left over of the 48 and a 3 left over from the 18. And then all we do with the variables is essentially the same thing. We have x to the 4th power. You don't need to do this graphic if you don't want to do this graphic. So x to the 4th power, x to the 5th power. I can clearly see they share 1, 2, 3, 4 x's. So if they share 4 x's, x to the 4th power can go to the outside. Well, we look back at this, x to the 4th. Well, it gave away all of its x's, so it has no x's left. So that 8 is a constant value. So this would look like 8 minus 3. Now, the x to the 5th power gave away 4 of its 5, which means it has 1 left. That 1 stays right there. So that is me using the factoring tree to find a GCF. The GCF is 6x to the 4th power. If the question says, what is the GCF? That's the answer. If the question says factor the GCF, that's what we do. All right, and I had another one here. Only thing that's really different, one main thing that's different about this is the fact that there's a negative sign. If you don't like negative signs, you're more than welcome to just pull the negative sign out to start the question. But remember, it changes everything, even the 36. Let's actually take care of the variables while we're at it. Let's do that. You can't pull out more than the least one has. So I could pull out x to the third power. If I do that, there are no more x's attached to the 81. If I pull out 3 x's from x to the fifth, we still have x squared. Now you notice my 81 turned positive because I factored away a negative sign. Anytime you factor away a negative sign, the sign changes. Here's something else to think about as well as you do these. How many more x's did the 36 have? From 5 to 3, it had 2 more x's. When we look down at my factored form, 2 compared to 0, it still has 2 more. It's very important that that stays consistent. All right, let's do the factoring tree to factor down our 81. So that's 9 times 9, which is 3 times 3, 3 times 3. So essentially what 81 is 3 to the 4th power. Remember, mark these out after you factor, otherwise you'll be doing them again. 36, 6 times 6, 2 times 3, and of course 2 times 3. So then I just look and see what they share. Whatever they share goes to the outside. I see they share a 3, and then I see they share a second 3. So what goes on the outside is 3 times 3. And then the x to the third power is with them. We look at the 81. What's left of the 81 when we pull a couple of 3's? Well, 3 times 3, 9. What's left of the 36 when we pull out a 3 times 3, or 9? What's left is 2 times 2, 4. And this is x squared. 3 times 3 is negative 9, so here is our factored. There's our GCF, negative 9, x to the third, and our factored form would be that.